Welcome to Physics for Students. My name is Shaunak and we are starting with a new video on topology which is called product topology. With product topology there are certain related concepts that we are going to learn, that is projection maps and something very interesting which is called factoring topological spaces. Before we start with product topology, whenever we are talking of the term product, what immediately comes to our mind is that what is a product, and we all know, we have been doing product since our school level mathematics, that it is basically multiplication. So first in this video what I am going to do is that I'm going to start with what is called a Cartesian product. Don't get bored, don't skip this video, because I always start with simple related concepts, because once we understand those concepts things become clearer to us and the concepts of product topology will be much easier to understand. Okay, so what do we mean by product? In general, in mathematics, product we mean that it is a number that we get by multiplying two or more other numbers, right? This is very simple. So when 2 is multiplied by 6, we give something called a 12, and these 2 and 6 are the factors and 12 is what is called the product. So what we can say is that we can find each product of a number by multiplying it by another number. It can be big, small, certain parts, doesn't matter. Now when we talk of product, we can also find this to be a product A multiplied by B. You can see the horizontal and the vertical A and B contains elements as 1, 2 and A, B, C. This is a nice funny picture. It's a cat and a dog and a milk. I think that would be chicken or something. So A and B, when it is multiplied, it gives to dog with a chicken and the cat with a milk, and finally with the cat with the chicken. So we get something like this with the X, Y, Z and B containing 3 elements. So when we put it a kind of a matrix, or we put in terms of set, we multiply the first element of A with the first element of B, this first element of A with the second element of B, and the first element of A with the third element of B. So this is just to give you an overall visual and understanding of what do we mean by a product in terms of Cartesian coordinates and in general. Now when we talk of topology, what is most important that we build with set theory and what is called the Cartesian product of sets. Now Cartesian products of sets, we will take two sets, for example X, and then we take Y. So the Cartesian product of X multiplied by Y between two sets X and Y is the set of all possible ordered pairs with the first element from X and the second element of Y, which can be written in mathematical term as this. Now just hold on, if you are reading this right, this is all possible ordered pairs. So those who were aware about set theory in general, so you know this ordered pairs can also be written in terms of ordered sets. So this is the first indication that how from the very basic foundation of Cartesian products we are going towards a set theory. Now one example is the standard Cartesian coordinates of the plane. For example, let us consider X, which contains certain blue dots, and I call this the set of points on the X-axis, and Y as the set of points on the Y-axis, which is this blue dot, and this is the X and Y plane. So what I can say is that this X multiplied by Y is the XY plane, right? This is the XY plane. And if I take X equals to Y, we can denote the Cartesian product of X with itself as X multiplied by X gives to X squared. So for example, if we this is just a pretty simple example. So if we can represent both X axis and Y axis as the set of real numbers, then we call it R, and we can write the XY plane as R times R, which gives to R squared. Okay, so we just denoted XY in terms of set theory definition, and then we got the XY plane as a real number set R, and how we can write is as R squared. Okay, so we will just touch base on certain properties of Cartesian product. We know that Cartesian product is non-commutative. So we get two sets A and B, and we are going to show A multiplied by B is not equals to B multiplied by A. So we will take A as 1, 2, B and 3, 4. Then we multiplied A by B, which A multiplied by B, which gives this, and B multiplied by A, which gives this. And obviously it is quite evident that A multiplied by B is not equal to B multiplied by A. This is just to touch base on the properties of Cartesian product. I know that you already are aware about these things, but there is no harm in just doing those. Okay, so we come to the next one, which is Cartesian product is non-associative. So A, B and C is not equal to A multiplied by B multiplied by C. So we take A, if A equals to 1, then this comes to be so, which shows automatically this is not equal to this. But we have to be aware that the Cartesian product is not associative unless one of the involved sets is empty. So that is how the non-associative property comes in. Okay, further going, we know that the Cartesian products satisfy the following properties. It will satisfy with respect to intersections. So A intersecting with B multiplied by C intersecting with D is not equal to A multiplied by C intersecting with B multiplied by D. This figure, or the photograph, I would say figure, more or less shows this, and this is also the same, the second one. Right, but remember that in most of the cases this statement will be replaced, and it is not true if we replace it with union. And you can see A union of B multiplied by C union of D is not equal to A multiplied C when it is taken with union with B multiplied by D. Okay, so this is just to say that this I would say this intersection, when it is replaced by union, doesn't follow. Okay, so these are few of the rules, and we have this rule as distributive property over set of intersection. You can check distributive property over set of union, that is also true, and absolute complement, which is denoted by this C. So these are different properties of the Cartesian products, and I just showed you what are those things. Okay, now for the time being, as we approach product topology, I really want you to forget about topology. Okay, so let us forget topology for a moment, and let us take a step backwards and consider the function, this one, fx comma y equals to xy. Now just hold on, why I am telling you function and then going to topological products, it will become easier to, it will quite become clear. So just hold on, don't skip this part, otherwise it won't be clear for you. Now when we look at this function, this one which is right on your screen, we typically think of its behavior as the variables of x and y which are varied separately. You can see x and y are varied separately. That means that is for a fixed value of x, we can observe the change in the function where we can vary y and vice versa. Okay, so for a fixed value of x, we can observe that the change in the function, and for y, if we vary, it is the same. So in this sense, what we can tell is that f of xy, we are using this as a factor of the function f of xy, right? So in some way, we are factoring this particular function. So we know that factoring means finding expressions that can be multiplied together to give the expression on one side of the equation. Okay, so this is basically factoring. Now why I am using functions and showing factoring, it will become very clear to you. Okay, now we come to the most important concept, which is called factoring topological spaces. So what do we mean by factoring topological spaces? So we tell that when we use factoring, we mean when we break down a number into smaller numbers, so multiplied together gives back to the original number. Right, so when we split numbers into factors or divisors, that is a factorization. So for example, factoring the number 12 into 3 and 4, we get this one as a big number and these are the small numbers. Clear? So now hold on, this is actually the main crux of the video. So we are using small numbers, okay, to get hold of a big number. Now if we take a kind of a topological space T, for example, the blue one. So what we can do is that we can break this original topological space, and when multiplied, it gives back to the original topology. So we get T1, this one, when multiplied by T2, and when multiplied by T3, for example, gives back this T. I hope this is pretty clear, right? So this one can be formulated as getting back the T as T1, T2 and T3, just in the same way 3 multiplied by 4 gives to 12. Remember, this is just an analogy to make things clear on an intuitive way. Don't go by the rigorous definition. We will come to the mathematical part later. So this is what I'm trying to tell you, that when we talk of product topology, it is basically product of this T1 and T2 and T3, which multiplied by these factors gives back to the original T. So now if we take, for example, definition of a Cartesian product, and with our picture it agrees with the this kind of a real line, right, where there's an x coordinate for the first r and the second coordinate. So what we can do is that when we multiply r multiplied by r, it gives to r squared. Okay, so this is what I'm trying to show you, that the picture actually representing points as having coordinate from the first r in the x and the second r into y, then it gives to r squared. Okay, now we can apply this simple intuition into defining or telling that topological spaces can be factored. Now, for example, factored means I'm dividing it into further, right? So, for example, the topological spaces that can be factored as the product x multiplied by y. So, this is something which are the blue dots are the points, right? And I call it as x comma y, which is a typical Cartesian pair x comma y. And we take another topology y, for example, these also contains blue dots, and these are also represented as Cartesian pairs x and y, where each x is an element of big X and small y. I mean, the points are an element of big Y. The spaces x and y are typically become simpler and more familiar and more easy to visualize. But this won't be so. There will be further complex situations and complex spaces where these things will not work. But anyway, this is a kind of a nice and an intuitive way of understanding how the products when accumulated together gives back to the topology and how it happens. Okay, now intuitively we will take a cylinder, right? For example, we take this this kind of a cylinder. We will deal with this much later, but I will just explain to you. So this cylinder, I can take the base of the cylinder, right, the radius r. Okay, so on the surface of the cylinder, which we can see you right on the right hand side of the screen, can be thought of as a circle extruded down the length of the interval. Forget about the length of the interval, the length. It is extruded down. That means the bottom part is there. And now what we do is we construct this and this and this, and we get a complete cylinder. Are you getting my point? So this is how it happens. So this gives back to this. So we are using the extruded surface of the circle in order to construct a cylinder. So it is a kind of a we are using the small numbers in order to get back to the original number, just like 4 multiplied by 3 gives back to the 12 number. And we can do the same with torus, right? This is the torus and this is the outer part. So we can tell that the torus can be interpreted as one small circle extruded around the circumference of a second larger circle, and in this way. Okay, we'll come to these parts later. I will really show you. Now, so the concept is that exotic spaces can be built, okay, out of familiar ones by taking products. So ultimately, you can say that there are an infinitely large number of ways to combine such spaces. For example, this disk, and for example, this sphere, the torus, the projective plane, which I have not shown, and so on. So this gives you at the beginning of this video a kind of an intuitive understanding that what is actually product topology and how the product are giving back the topology. Just in terms of Cartesian products, it gives back to the original number. Okay, so what we do is that now we come to product topology definitions. This will be the mathematical definitions and things will become clear. We will take forward 2 definitions. First, we start with the first definition. Okay, so here is the definition, that the topology on the Cartesian product x and y of 2 topological spaces whose open sets are the union of subsets A multiplied by B, where A and B are open subsets of x and y respectively. So let us see how we can understand this definition. So we take one set, is the topological space X, and here is another topological space Y, okay, and here is A and B, which are open subsets, and A is an open subset of X and B is an open subset of Y. Okay, now this definition, what I did on the right hand side is that we extended this further. So definition is extended to the Cartesian product of any finite number, say for example n, onto topological space. So the product topology would R multiplied by R multiplied by R, and would go up to n times, where R is the real line in the Euclidean topology, and it coincides with the Euclidean topology of Euclidean space Rn. So if you really don't understand what is an Euclidean space or an Euclidean topology, you can find it in the playlist of my videos on topology. You can look into it, things will become clear. However, this part is also, I think, clear, that how we can take the natural, any finite number up to n, and we can construct R as the real line of Euclidean topology and Euclidean space. Okay, so what do we get in the definition of product topology? We get this, right? So you all know this is basically the product part, and what I get is that we consider I to be any set, right? The open sets are the union of subsets of, the open sets are the union of subsets, which is this one on the left hand side of the screen. And I say UI, this one, U sub I, is an open set or open subset of X sub I, right? With a condition that UI, your U sub I, will be equal to X sub I for all but finitely many indices. So for example, I take this as I is a finite set. So now the reason for this choice of open sets is that I mean to say, at least needed to make the projection of the ith factor. So we showed P sub I as a projection of X to Xi, continuous for all indices I, right? This is continuous, remember, for all indices I. Now, admitting that all products of open sets would give rise to larger topology, right? It actually gives back to something very interesting, which I am thinking to make. It is called I, when it is infinite set, it is called box topology. Okay, now what is box topology? We are not going to show it right in the video, but I'm definitely going to show the basic essentials of box topology. Now this is also called Tychonoff topology, but remember, it is not the notion with Tychonoff space that is different. So product topology is also called Tychonoff topology. So you understand this from the first definition, that, and remember that if I goes to infinite set, this falls and it becomes a product in kinds of a box topology. Okay, fine. So regarding box topology, as I told you, I'm going to make a video. So just let us understand, for finite product spaces, when it is finite, box and product topology are more or less the same. Okay, this box topology is finer and product topology is coarser. This part, this one, the product I is an element of big I. The product topology is generated by sets from this one, where each U sub I, remember, it is open in X sub I. Each U sub I is open in X sub I, but for most finitely I, UI is equal to X sub I. So this is important when we are talking of product and the box topology. This part is important. Each U sub I is open in X sub I, but it is finite. That means it is limited up to a certain extent. So as you have seen, that I have written that in other words, we can tell almost all the factors has to be integrated into an entire space. So in the box topology, each factor of U sub I has just to be open in X sub I, which means that in box topology there are too much amount of sets, right? And to generate a topology, we need a finite intersection of sets, but not infinite intersection. So box topology adds in open sets that are not required in this context. Okay, so this is basically what is box topology and product topology. So to generate a topology, we need finite. So you see 1, 2, third line from the top of the screen, I have written most finitely I, U sub I equals to X sub I. So here it has to be finite, but in case of box topology, it goes infinite, so it is not required. So this gives you just an idea on product and box topology. Okay. So we are now, we have got the certain mechanism to combine spaces using products. So our next step is to extend this picture to include open sets and open topology. Okay, so in order to make this kind of a C, we observe that if U and V, for example in this figure, are open sets in the component spaces X and Y, right? U and V are open sets in the component spaces X and Y, then as we all know that U multiplied by V should be open in the sets of product X multiplied by Y. Making this as a requirement means what we can do is this figure. These are the these are what we call open sets, and we have just taken an arbitrary, because I want to show you that using this we can actually build up arbitrary open sets in X, adding up arbitrary open sets in X and adding up open sets in a base for its topology. We can likewise build up arbitrary open sets in X multiplied by Y as the union of open up sets in the form of U multiplied by V. I think this is clear. So what I am trying to show you is that we can build up arbitrary open sets, adding open sets in a base for its topology. So the collection of such sets U multiplied by V is called to be the family of B. You remember that B, that this curly B earlier in the video we mentioned to be the basis, right? And the finite intersection of members of B also lies in B. So the collection, this curly B, is therefore a base for a topology on X multiplied by Y, and that is appropriately named as product topology, right? We can also say that X multiplied by Y is paired with this topology. It is called product space. Anyway, so you can, if you have seen the earlier video, this curly B has been represented as the basis. So what with this right now is that we built the basis, right, the family B, and the finite intersection of members in B which also lies in B. So therefore the collection has a base and it can be called as a product topology. So this gives you a kind of an idea of the first definition of what is a product topology. Okay, now we will go with the second definition. Why second definition? It will become clear for you. So what is the second definition? It is this. So if X and Y be topological spaces, the product topology on set X multiplied by Y is the topology having the basis as the collection curly B of U and V, where U is an open subset of X and V is an open subset of Y. Okay, now let us see that considering this definition, can we meaningfully prove this one? So let us suppose that X and Y are open, right? X is open and Y is open. That means that X multiplied by B will include the basis B, right? So the first part of the definition is being proved, right? It is satisfied. Now for the second part of the definition, we will consider B1 and B2 equals to U multiplied by V1 and U2 multiplied by V2. And these are the elements of B, this curly B, right? Then what happens is this condition is a basis of element, right? U1 multiplied, you have seen this earlier, right? U1 multiplied by V1 intersection with U2 multiplied by V2 equals to this intersection of U1, U2 and V1, V2, right? Forms the basis of element of V. Then what happens? U1 multiplied by V1 intersection of this equals to this one is open, is a basis element, and it is open in X and Y. So what I'm trying to tell you is that the topmost condition of multiplication used in using the intersection forms the basis element. Why? Because of this one. U1 intersect with U2 and V1 intersecting with V2 are all open in X and Y. Okay, so this is one figure which will make this part clear. Which part clear? This one, the long equation part you see here. Okay, the intersection part is clear, right? And we can see this one which is in yellow, and we see this one also. But remember that the union of the two rectangles, which is given in black and white, which I have taken from Mooncrest, right? This union of the two rectangles, this is not a product of two sets, so it cannot belong to B. So however, it is open in X multiplied by Y. So it cannot belong to B, but however it is open. This is a kind of an example. so that the intersection part become clear, and this is not a product of two sets. Okay, so in simple words, what we can say is that the product topology on X multiplied by Y is defined to be the topology generated by the base, this one, where X comma V is open in Y. Okay, so in other words, what we can say that if, for example, X and Y are the two sets, this is open if and only if it's the union of open rectangles in the form U multiplied by V, right? So this is how, and this U is open in X and V is open in Y, right? So this one U is open. This will be represented now. We will replace these variables as U1 and U2, but currently let us consider U is open in X and V is open in Y. Okay. Now here comes a big question. Now, what is that question? Can you guess? Can you just let me know in the comment box? Did you guess it earlier? Okay. So the question is that, say for example, X and Y is considered to be open in the product topology, right? If and only if we have shown that it is rectangle. Now, how is the product of X and Y, right, is related to the topology of X and it is related to the topology of Y? Right. So X multiplied by Y is basically the product topology, right? Now, how is that this X is related to the topology individually of X, which we call is which we will call as X1 and X2 in the next part of the video for simplicity. So how it is that this one is related to this one? That is the big question. Now, how is the product of X multiplied by Y is related to X and Y? Okay, so this actually gives us an option to move sets from X comma Y, X multiplied by Y into the constituent sets of X and Y. So we are introducing a concept where the sets are now being dealt as constituent sets. That means the X multiplied by Y, how it will relate to individual. That is why the AND part I have written it in red. So this is the big question. So the answer is the direct relationship comes through projection maps, and that will be the next part of the video where we are going to understand what is a projection map and how these topologies are related. Projection maps. Now, I'm not going to explain in details about projection maps because you already know, which uses, the image of the Earth and then the Mercator and other things. But here is what is a basic idea of what is a projection. So a projection is the transformation of points and lines in one plane into another plane by connecting corresponding points on the two planes. So you can just visualize this figure as shining a light source through a translucent sheet of paper and making an image of whatever is drawn on it on the second paper. So we know that the branch of geometry dealing with those geometric figures is called projective geometry. Okay, here is the definition which you can read later. Projection is a transformation of points. We also know something about vector projection, and a vector projection of a vector of A onto a non-zero vector B sometimes is denoted as this proj sub B of A, and we can see this figure which actually shows projection of A on B as A1 and rejection of A from B as A2. We can further find out that in an orthogonal projection of A onto a straight line parallel to B, it is a vector parallel to V which is denoted as this, and this figure also shows 90 degrees less than theta less than equal to 180 degree. A1 has an opposite direction. It shows the opposite direction of B, and in case of A1 is a scalar, we call the scalar projection as cos theta. A dot B, where the dot denotes the dot product. Okay, so this gives you a kind of a basic idea of what is projection. The definition of projection is this. So let pi 1, this one you can see the equation equals to x, and this one would be the equation which is equal to y. So the maps pi 1 and pi 2 are the projections of x and y onto its first and second factors respectively. So here will make the viewers aware when I am using onto, I mean to say pi1 and pi2 are surjective, right? So unless one of the spaces x and y happens to be empty, x and y is empty, and our whole discussion will be absolutely fruitless. So this is basically an onto surjection, mind it. Okay, yeah, so it shows that it is surjective. Okay, so we go further, and what we find that if U, for example, is an open subset, then this set, which is precisely the set U multiplied by Y, okay, which is open in X multiplied by Y, and if V is open, right, then this comes true, which is also open in X multiplied by B. So what I'm trying to tell you is that this is the figure. So this actually speaks of what is called the inverse image. So you can see this figure, the inverse one, the red and the blue. So we start from here and we reach up to there. This is the inverse image, and again we start from here and we reach up to here. So this is actually what it shows. So the inverse images of open sets X and Y under projections can be used to create something which is called a sub-basis, which we are not going to deal with this part of the video, but just to show you, this is what the open sets in X and Y under projections, how it takes care, right? Now there is a theorem, a simple theorem, which you are going to prove in a very simple way. So the projections of pi1 and pi2 are continuous and open. Now in order to prove this, what we do is that the inverse image of an open set in x1 is open in x2, right? So we have to show this one, which is written in blue. The upper one, curly one, is the theorem. The theorem says the projections are continuous and open. Now to show that the inverse image of an open set, this is x1 multiplied by x2, what we do is that we take an open set u1 in x1. Okay, the inverse image, this one, is a set of all points of x1 and x2, obviously, which actually projects down to x1. That is why the arrow shows towards x1. Now if you think about it, that the set is just u1 multiplied by x2, right? Since u1 is open in x1 and x2 is open in x2, u1 multiplied by x2 is open in x1 multiplied by x2, because it is open, and hence pi1 is continuous, right? So this is the first one which shows that this is continuous. Pretty simple. So I just took the sets and I did the open set of u1 and x1, and I showed that. Now in order to show that pi1 is open, what we will do is that take an open set v in x1 multiplied by x2, and we have to show that this one is open. So we can write this, right? Remember that this is A is the index set, okay, and it is it doesn't matter whether it is finite or infinite, it doesn't matter. And for each of A, which is an element of A, this u which is going from 1 to infinity is an open set in x1, and 2 is an open set in x2. So we can assume that the sets, these are obviously non-empty sets. We have to assume these are non-empty sets, and from this it is quite clear that this one, for each A, alpha is an element of A, right? We get this. It's quite simple, right? Simple calculation. And the right hand side, which is marked round in red, this one is the union of open sets, and is therefore it should be open, and it proves that pi1 is open. You can take a snapshot if you want, because there are a lot of calculations, I understand, involved in it, but this is how it happens. So for each alpha, which is a element of A, we take x1 and x2, and then we do the calculation, and then for each alpha in A, we take this part and we show this right hand side union of open sets, and thereby pi1 is open. So this proves actually the earlier one. So if we go back to the earlier one, so yes, this one, pi1 is continuous and open. Continuous part is proven in here, and the open part is proven over here. So now you see the utility of product topology, right? So it carries a lot of meaning, a lot of sense. So what we can say finally, that the projections of pi1 and pi2 are continuous, and we can say it is the smallest topology with this property, we threw in the barest minimum open sets, which we call x1 multiplied by which are required to make these maps continuous. Also we can say that if we made it smaller, if we make it further smaller, pi 1 and pi 2, it would have failed. And most importantly, this one, we can say if x1 multiplied by x2 have whatever this property means, whatever be the property, then x1 and x2 individually will have this property, obviously. So if 2 multiplied by 6 gives 12, then whatever the property is in 2 and whatever the property is in 6 will eventually gives into 12. That is quite evident, right? So conversely, what we can say that if x1 and x2 are connected, then pi this one is also connected, since the image of a connected set under a continuous map obviously remains connected. But remember another thing, that this one is also this one equals to x1, so x1 is also connected, and similarly x2 is connected. Okay. So this gives you a kind of, what I would say, you can call it a utility of product topology, or what we conclude with the product topology, and how these properties of x1 and x2, once we understand the behavior of those, gives rise to the individual property which we can learn. And we also can learn the connectivity. If this is connected to this, then this one is also connected, and so on. What we also come to know is that if x1 and x2 have both similar topology, so x1 has the same topological property as x2, then one can usually prove the same property for the product x1 multiplied by x2 also have the same property, right? So I would repeat, x1 and x2, if they have both the same topological property, then one can usually prove that the same property for the product which I have shown, x1 multiplied by x2. Let me give you certain simple examples. The product of two sets is connected sets, so that is quite a product of two connected sets is connected. Two Hausdorff spaces is a Hausdorff space. The product of two compact sets is a compact, and so on, right? I am not going to prove this, right? So x1 and x2, but remember one thing, that x1 and x2, here it is doesn't actually contain x1 and x2 directly. What it contains, that for every let me read it for you. So x1 and x2 does not actually contain x1 or x2 directly. That it doesn't contain x1 and x2 directly. This is for every x2 which is an element of big x2. x1 and x2 contains the set x1 multiplied by x2, which is homeomorphic to x1. And obviously I'm not going to prove this right now. Okay, so this is a kind of an understanding that I mean to say, if from the product spaces, what are the things that we come to know? Multiplication, individual, product of two connected set, product of two compact sets, and lastly what I showed you, actually x1 and x2 doesn't contain x1 or x2 directly. Okay, so x1 multiplied by x2 consists of pairs of elements, whereas x1 and x2 consist individual elements. This is very important. x1 multiplied by x2 consists of pair of elements. They are pairing, while x1 and x2 consist of individual elements. However, for x2, which is a family member of x2, x1 and x2 contains a set which is homeomorphic to x1. Okay. Now we will come back to that part, what I was trying to show you, the cylinder part, and what actually it leads to. So this is a kind of a nice cylinder, height and radius given, and this is multiplied by u by v. This is a point, right? X and y, right? And what is happening is that we have taken this as an interval. So this pi 2 is basically the projection which we have just seen, the projection. So y equals to 1 is basically the interval. We are taking this as an interval, right? And then we can represent this one going further and creating an ellipse kind of a thing. So the extruded part, what we are talking about, and this is u with the interval dot point, this is x, and we can tell CYL, which stands for cylinder, equals to S1 multiplied by I. Now see this I, this one is the circle in the xy plane, and this I is actually the interval. See how beautiful it is. Isn't it so beautiful? So we constructed this cylinder, okay, we constructed this cylinder based on the interval and extending this line as pi1, which goes down bottom where this small circle is there, and the left hand side this pi2 goes towards the y part, which is an interval. And that is why we can say cylinder equals to circle in the plane, which is s1 multiplied by I. Okay, and we can tell s1 equals to x. So let us see the similar kind of an example with the torus. So here is the torus u and v. This is the inner circle. This is x and y. I further extended it to pi1. This one is s1 is equal to x, and this one which extends up to v. Now remember, this torus can be interpreted, right? So this torus, what I can say, that it can be interpreted as one small circle, that round, the blue one, extruded around the circumference of a second large circle, and s1 equals to y, and we can call torus as a multiplication of s1 multiplied by s1, right? So if you want to see it again, this is really beautiful how we really construct them. So this is how the cylinder and the torus are being represented as product spaces. The cylinder is extended from the lower part, and the torus on this part, which can be said as s1 multiplied by s1, and s1 is basically the circle in the plane, circle in the xy plane. Okay, so let us see these two pictures together once, this one and this one. Okay, and what we can say, that the cylinder and the torus can be represented as product spaces. Right, this one, cylinder, and it can be represented as product spaces. So the notions of product spaces can be made concrete by comparing these definitions of the figures, and it is now complete. The definition lies right in front of you. Want to take a snapshot, etc., you can do that, but this is how it happens. Okay, so that was all, quite an extensive video on what is called a product topology. So quick summary, we learned, first started with Cartesian product of sets. We then went into properties of the Cartesian products. We learned what these Cartesian products leads to factoring of topological spaces. The two definitions of product topology. What is a projection map? Before that, we understood that big question, that why x and y can be individually dealt with the topologies of x and y. What is a projection map, a simple theorem, and a proof, and finally the summary. So that's all. I think you have liked this video. If you have any question related to this, please put up your comment in the comment box. Please do like, subscribe, and click on the bell icon, and click on the all button to get all the notification from Physics for Students. This is Shaunak signing off from Physics for Students, promising to come very shortly with another interesting video on topology. Till then, goodbye and have a nice weekend ahead.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.